And we're back for another lecture on electrochemistry. Hopefully you've already completed your work for our last lecture, 20Nov18a video. That would have been CA48. Also, make sure that you're taking a look at the content page for Canvas. It's got a lot of great resources. You'll want to have on hand paper, calculator, pen, or pencil. All right. First, let's start with a review. Remember, we've been talking about volcanic cells. These are spontaneous. We get electrical energy out, but we don't have to put any in. We're getting that energy out because we've done some clever chemistry. Taking a look at the cell again, remember that oxidation occurs at the anode, reduction occurs at the cathode. We've got our nice reduction potential table. Stuff at the very top likes to be reduced and are really good oxidizing agents. As we move down the table, things really want to be oxidized more, especially the stuff at the bottom, and they're really good reducing agents. Some more concepts to review from cell potential from last lecture. A half reaction with a strong tendency to occur has a large positive half cell potential. That's the stuff at the top of the table. When two half cells are connected, the electrons will flow so that the half reaction with the large positive half cell potential will occur. Think back to copper zinc. Copper had a larger reduction potential, so the electrons flowed from zinc to the copper 2+, so it could be reduced to form copper solid. Higher on the table, stronger tendency to be reduced. Lower on the table, stronger tendency to be oxidized. Now remember our old example with our zinc and our copper. We had our two half reaction potentials. Now we take a look at those half reactions and we notice right away that for zinc, the reduction has a negative cell potential. That means in relationship to the copper, it's not going to happen in that direction. Zinc isn't going to be reduced in this case. Zinc is going to be oxidized and copper 2+ is going to be reduced. Under these conditions, we're going to get copper 2+ being reduced to copper solid, zinc solid being oxidized. Zinc is going to donate electrons to copper 2+, and our electron flow will happen as depicted here. Now, let's talk math. We want to know how much energy we're going to get out, because remember, we're generating electrical energy, and we need that electrical energy because we want to keep the lights on, our cell phones charged, our batteries starting, right, for our cars. We might, hey, maybe even we have an electric car. We want to be able to make our breakfast smoothies, whatever. We want that energy. So how much energy are we going to get out? That's why we calculate the cell potential of an electrochemical cell using the equation showed here. Your E cell is going to equal your E oxidation plus your E reduction. Let's take a look at an example. This reaction shown here. We've got solid aluminum, nitrate, and we've got some H+. So it looks like maybe we've put some aluminum in nitric acid. What do we get out? We get out aluminum 3+, we get out nitrous oxide, we get out water. Now, take a look at those oxidation states. It definitely looks like something's being reduced and something's being oxidized. I mean, take a look at aluminum. It's gone from having an oxidation number on the left of 0, since it's in its elemental state, to losing electrons to be Al3+. Let's dig deeper. Well, we take a look at our two half reactions. The oxidation was easy to spot because it's the solid aluminum, aluminum 3+, then we get our out 3 electrons. Now the reduction took a little bit of investigation. But we take a look here. Remember that our oxygens, the stuff that we're going to be looking at, the oxygen is a 2 minus. You've got 3 of them. Okay, well, then that means that for this NO3, that all the oxygens would be a -6, but then you see how there's the minus sign, so that means that that nitrogen in particular, right, is a +5. Now, you've got your other side nitrogen, and we see that the nitrogen in that case, for just the NO, yes, there is a real compound called NO, and that oxygen is still a -2, but now the whole compound is neutral. And so that means that the oxygen's a -2 and the nitrogen would be a +2 to get you that neutral NO compound. So the nitrogen in the reduction half reaction on the left was a +5. It's been reduced to a +2, which means it's gained 3 electrons. Nothing is happening with the oxygen or the H+. They're just kind of hanging around to balance out some charges. So we take a look at our table. And that table is the one I provided earlier in the lecture. And you'll always be provided a redox table like that. So if we take a look from our half reactions, we see that aluminum really does not want to be reduced. Take a look at that negative reduction potential. Woo! -1.66. That means that aluminum really wants to be oxidized. It wants to go the other way. But if we take a look at the nitrogen half reaction involving our nitrate in acid, we see that, hey, that reduction, that's positive. And in relationship to the aluminum half reaction, it's large and positive. So this is going to be the reduction that occurs. And what's going to happen is that aluminum is actually going to get oxidized. So we're going to run that reaction in reverse. And that highlighted set of reactions, that's going to be the combination that occurs. The reduction, again, is going to be that top half reaction in the box. And our oxidation is going to be the one right below it for aluminum. So it's as simple as now adding those two together. And we're going to get out 2.62 volts. So keep in mind what we did here. We actually looked at the reduction potential table and we wrote the half reactions in the direction they would actually occur based on what the reduction potentials were. The reduction potential for the nitrate was big and positive relative to the reduction potential for the aluminum, which was negative. So the aluminum reaction gets run as an oxidation reaction, which changes the E reduction to an E oxidation, a positive value of 1.66. We then add those two values together and we get our E cell. So we're going to get out 2.62 volts. Not bad for a day's work. So let's take a look at Chem Activity 49, which will give lots of good practice on the cell voltage. Pause the video, read Model 1, and complete CTQ number 1, all of its parts. Don't skip these questions. All right. Let's talk about predicting spontaneity of redox reactions. A spontaneous reaction will take place when the reduction half reaction is paired with an oxidation half reaction lower on the table. Back to our old friends, copper and zinc. Remember, copper was the one with the large positive reduction potential. It was paired with a half reaction much lower on the table. So The copper 2 plus is the one that's actually going to be reduced, and the zinc is actually going to be oxidized. And this is the reaction we're going to get. It's spontaneous. You put these two together, and again, they go together like peanut butter and jelly. They're going to want to work. The zinc's going to give up its electrons to copper, and we're going to get out some nice voltage. Now, what would be non-spontaneous is that if we tried to run it in reverse, where this really doesn't look very nice. Your copper is actually being oxidized and your zinc is being reduced. Well, this would actually require us to put in energy because that is not the way this reaction wants to occur. It is absolutely non-spontaneous. So a spontaneous reaction is one that has a positive E cell. A non-spontaneous reaction will have a negative E cell. You want to think about that as like a bill, a negative balance. That means you owe. And in this case, you'd have to put in energy to make the reaction work. You're not even going to get out any. So we take a look at these numbers again. It's only when we run it in this particular way, where copper 2 plus is reduced and zinc solid is oxidized, that we get a positive E cell, which is spontaneous. And we get out 1.1 volts. If we try to run it in reverse, we are going to get out negative. That means that we're not going to get out anything. We're going to have to put in that much voltage to make this thing work. Let's take a look at another example. We've got these two options here. Iron solid, we've got magnesium 2 plus going to iron 2 plus, magnesium solid. Well, this would mean in that top reaction that you've got iron is being oxidized, magnesium is being reduced. In the bottom reaction, you've got solid iron, lead, and take a look. Iron is still showed as being oxidized and lead is being reduced. Now, is this going to be spontaneous? Let's take a look. Well, first we look at that first reaction, iron and magnesium. Let's take a look at the half reaction for the reduction of magnesium. Whoa! Negative 2.37. Ooh, that is low on the table. If we remember from that table I showed you, magnesium is like way at the bottom. Now take a look at iron. Yeah. Now, that's the reduction, right, or the oxidation of iron. It's negative, which means it really does not want to occur as an oxidation. In fact, it wants to occur as a reduction. You see that negative sign for the iron oxidation, remember, we can flip it around and we'd get the reduction potential. The reduction potential for iron then is positive, and magnesium is really not. So the way this reaction should actually run is not the way it's being written here. That top reaction is non-spontaneous because iron should be shown being the one that's reduced, not magnesium. So how it would actually go is that magnesium would be the one being oxidized and iron 2 plus would be reduced. This is the way it should actually work to be spontaneous. The way it's written at the top, that is non-spontaneous, and that is going to require you to put in a lot of juice. Now, let's pause the video here. Think about the example that we just worked through. Pause the video and complete exercises 1 through 3 on Chem Activity 49. Complete problem 1. You'll want to use the standard reduction table on today's content page in the assigned reading, or there is a reduction potential table offered to you through Mastering Chemistry. Use any one of those sources to complete the problems. Do not skip these questions. Mastery of the material just comes with practice. Looking ahead, make sure that you're completing all of the work in each of the videos for today, A and B. Keep an eye on your Mastering Chemistry due dates. And hey, there's an extra credit electrochemistry quiz on Canvas. And rewatch these lectures as needed. And remember to do your required reading and materials on the content page, especially the video that was posted from Boatsman Science. It's really good. Back on your reduction content page. All right, have a good break, get a bit of chemistry done, and I'll see you when we're back from break.